Hello everyone, welcome back to the Simple 3D Render series. In today's episode, we begin adding rotations into our code. These rotations will allow us to rotate objects and vertices in 3D space and allow us to begin to see our objects in a more detailed 3D perspective. So without further ado, let's get right into it. So before we begin coding and adding our rotations, we need to understand what rotating a object in 3D actually looks like, how we are going to do that, and looked at the idea behind it. So let's jump right over to our image. And rotating is kind of going to be familiar if you have a decent understanding of trigonometry. So let's jump down here and let's create a new little image. I'm just going to draw a line here so I don't get this confused. So let's imagine we are just looking at a normal Cartesian coordinate system, which we're all used to. So we have our x and the y axis here. And a lot of times, well, if you think about what rotations is, and the angle, it is actually a unit circle of some fixed radius r, which is usually 1. This is a terrible circle, but imagine this is uniform and nice. And an angle is just a point from the origin extended out to the another point in the circle. And that radius, again, is still 1, but it's just denoted r. And then you have some angle that intersects that will, which you can draw, basically trace back from the where the point is back to the origin, which is usually in this first quadrant here. So yeah, and then we know that these angles create a right triangle of some fixed length on its x and y axis. And the ratio of those sides and lengths, depending on, well, different ratios of those triangles lengths, can give you um, will be equal to the angle in which that triangle was created about. So that's usually the general idea of a rotation. And we know that the more we change the angle, right? So if we change the angle to be, that's roughly about 135 degrees, then the x and y points on that where that point intersects change as well. So that's just the basic idea of a rotation. But now let's actually understand about how we're going to rotate a point because, or a vertice. So a vertice we can imagine, let's just imagine we're looking at the y and x axis here. We'll ignore this circle. And we have some point right here. How can we rotate this point to, create the illusion that it's rotating? Well, to rotate it, we just would simply need to add an angle to this because again, we know that from the origin to that point, there would be some radius r, and there would be some angle that created that, I guess, pathway to that point, right? It would have some x and y components here. But if we wanted to move this point to, let's say, right here, or rotate it that way, we would actually have to add some angle to this, because this point has to go from there to there, which would be a difference in some angle. And again, this new point would still have some x and y component. But these x and y components here are important because these will denote where it moved to exactly. So how do we calculate this? Well, before we move the point, we would have generally the x component of that, of the original point, which would be this one right here. The original point for that would be equal to the radius times the cosine of the angle theta. And the y would be equal to the radius times the sine of the angle theta as well. So these would give us the components of the original point. But if we want to move or go to a new point, well, we have to, again, add some angle to it because you can see that we had the original angle theta, and as we added or put a new angle into it, we went to this point over here. So this total angle here is the new angle which we need to get to that new point. So what we'll do here is we'll label the new point x prime, and this would be equal to the radius again, times the cosine of theta plus alpha, which alpha here is going to be this angle that we changed from the beginning. and theta is our original angle we had. So these two added would give this total angle here, to which we can get that new x and y position of the new point as it rotated. And we'll do the same thing for the y position. So y prime would be equal to the r, the radius, times sine of theta plus alpha. So this is basically the fundamentals of how a point, or in this case, our vertice, will rotate. But the thing about these two equations here is that a lot of the times our alpha is unknown. So we don't really know how much we need to change to get to the new angle, if that makes sense. So what we actually have to do is, it'd be nicer if we could just tell an angle that we already have and be able to find the new point based off the angle. And you would say, well, how are we going to do this? Well, we aren't actually going to derive these new equations, but just know that these right here, specifically the cosine of an angle plus another angle, is used, well, it has a identity in the trig identities, and you can use those identities to simplify this equation, and then you can use substitution to derive a more simpler equation that only relies on some angle theta. Again, because alpha is generally not known. We don't know how much we need to move to get to a new point. So again, using tricks of identities and things that we're not going to do, you can I can link some additional resources in the description. You will derive to a new equation to find these x and y points based off just theta alone. So in this case though, I don't want to look just at the x and y here, because in today's video, we're going to rotate a object around the y-axis. So if I scroll up, this would look something like this. So imagine the y-axis going down this triangle, and all these vertices on the triangle are going to rotate around the y-axis, just like this. So if you hold up an object in front of you and you begin to rotate it, depending on how you are holding it, you're most likely going to rotate it around the y-axis. You'll notice that if you were to imagine the points of that make up that object, you would see that the y values of those points stay constant. And that is true in their picture here. As we rotate this triangle around the y-axis, the only points in space that are changing or rotating are going to be the x and z position. The y values stay the same, hence why we are rotating around the y-axis. So going down here to the rotation picture we drew, I'm simply going to, actually I'll just erase this whole thing. I'll keep these equations. So now I'm actually going to have z and z instead of y there. And our picture would kind of look somewhat the same. We'll have the x-axis and the z-axis, and we'll have some point here which we want to rotate. And so if we want to rotate this point by some angle theta, we'll use these formulas. So I haven't shown the formulas, and I'm going to show them right now. So the formulas are going to look something like this. So x prime here is going to be the new position, and the new position will be equal to the current position times the cosine of some angle we want to rotate by, plus the z position times sine of some angle we want to rotate by. Notice how y does not change. Again, we're rotating around the y-axis. The new z position will be equal to the inverse of the current x position times the sine of an angle plus z position times the cosine of some angle. So these three formulas right here are going to be our basis for rotating a vertice in 3D space around the y-axis. So let's actually begin implementing this into our code. So in our code, the first thing we're going to need to begin rotating is a angle. Right, we need some angle we're going to rotate the vertices by. So to do that, I create a global variable up top and name this angle, excuse me, and set this equal to 0 to begin with. The next thing we're going to need is some function to actually rotate this vertice. So down below in our previous functions, I'm going to create a void rotate function. And this rotate function will expect some vertice reference, which we'll just name vertice, some vertex reference, I should say. And in this rotate function, let's actually begin. This is going to be the function that, again, is going to rotate the vertices. And we're going to be using the equations we just looked at. So the first thing I'm going to do here is I'm going to create some local variable called angle radian. This is just going to be the radian representation of the current angle we're going to be rotating by. And the next thing I'm going to declare is going to be the new x position and the new z position. So in our code, I'm going to set the new x to be equal to basically copy and paste of the equation we have here. So the new x will be equal to the current x times the cosine of theta. So the vertice.x times the cosine of theta, which is needed to be in radians, so we'll use that there, plus the vertice.z times the sine of the angle, and then the new z will be equal to the inverse of vertice x, or the x position, times sine of the angle to radian, plus the vertice's current z position times the cosine of the angle to radian. So once we have these new x and z positions based off how much we want to rotate, we can just overwrite our current x and z positions with these new positions. So these new positions will be the new positions along the x and z axis as we rotate them. So now up top in our render stuff loop, notice here that I have a temporary triangle. Well, I have a temp vertex here. And you may ask, well, why are you doing that? Well, let's just ignore this for now, and I'll show you why. So in our render stuff loop, what I'm going to do is I'm going to call rotate here. And in rotate, I'm going to pass in the current triangle index we are on in the array. And I'm going to do the same thing to translate to screen. Next thing I'm going to do is I'm going to create a event key up top, and I'm going to check if the user or me presses the R key on the keyboard. And this R key will basically be the key to rotate our object. And all thing I'm going to do here is when the R key is pressed, I'm going to add to our angle global variable up top 1 degree. So that way when we call rotate, we will rotate this object. So if we run the program, we're going to get an error because I forget to put the declaration. So if we run the program, we'll see our triangles there. So if I press the R key though, notice what happens here. So as soon as I press the R key, the triangle begins to rotate infinitely, it appears, and it's just constantly rotating. So why is it doing that? Well, this goes back to what I had down here. What's happening is on each time this is processed, because remember, this is in a while loop, so this is constantly running. So on each frame, we're going to say, we call rotate. And when we go to rotate, we say, okay, there's a new angle, and the new x and z positions are going to be based off the current angle of rotation. And then we overwrite those vertices x and z positions to be those new rotated vertices, or rotated positions along the x and z, which is fine. But what's going to happen here is on the next frame, we're calling rotate again. And so remember, the vertices x and z positions have already been updated with the current rotation from last frame. So when we go back into this loop, we're rotating them again and then overwriting them again. So what's going to happen here is I'm just basically accumulating rotations to this vertice. And it's just going to keep rotating because rotation is being called every frame, and each frame it's going to rotate it some degree, and then the next frame is going to rotate it some degree again. So it doesn't matter about the angle being changed, it's just that this rotate is being called over and over, and it's accumulating those rotations to the vertices x and z position. So a way to counter this was creating a vertex temp, which will be equal to the current triangle vertice that is in the array. So what happens here is when we pass in this temp into our rotate and translate to screen functions, it's going to use the current vertice in the triangle array as a reference. So that way when rotate is called, it's only going to rotate that triangle vertex in the array by the angle that is being rotated by. And because before we were just constantly overwriting triangles vertices and accumulating a rotation to it. Now we're using the vertice as a reference, the original vertice as a reference, and we're going to rotate that original vertice by the angle we actually want to rotate it by. So now if we run the program, we'll see when we press R, that infinitely rotating goes away, and our triangle actually begins to rotate. But if you notice, our triangle is rotating in almost a arc fashion. It's like rotating around in a circle. So I don't know if you can see that here, but it kind of looks like it's like orbiting. So if we want to fix this, it's going to be kind of easy, but we need to understand what is causing this issue. So right now, looking at the top-down perspective of our y-axis, we have the x and the z, and we know that our points are going to be basically, all our points are at an offset of 0.5 from the z-axis, and we have 1 point on the negative 0.5 on the x, we have 1 on 0, we have another one on 0.5 on the x. So these right here are 3 vertices of our triangle from a top-down view. So the reason why we're getting this orbiting arc fashion when we rotate our triangle is because of the way the triangles are already positioned in space. So if we draw a line from this vertice right here, this is going to be the radius in which this object is going to rotate around. And as we rotate it, it looks normal, which is fine, which is supposed to be the bottom right of the triangle rotating. But once we go to the middle, we'll see that the object, the middle one, or the middle vertice, the top, the apex, is also going to rotate in some fashion. And this is the main reason why we're getting this arc orbiting fashion. So you can imagine kind of taking all these vertices and rotating them synchronous in sync. So you can kind of see that this is where the orbiting fashion is coming from. If you would imagine all 3 of these to move at the same time, they'd all be moving along this circular path. Which is fine because that's the main idea of rotating it, but it looks not right because all of them are rotating in an orbit fashion. So the way we're going to counter this simply, and I say simply because this does not work for all vertices of an object, this will work for what we have right now, but in later episodes we're going to actually implement a dynamic way to find where the triangle should rotate around. But for now, we'll just keep it simple. So to counter this the simple way, we're just going to set all of the z values of the vertices to be 0. So this will just effectively move all the vertices down along the x-axis. And I will draw these in green. And so they don't look much different besides from them being on some offset on the z value. So what this will do is when we begin to rotate it, so we'll start with this point. This point it will be rotating along this radius here, which will again create that same circular path. And the same thing for this one, which will create this circular path here. But notice when we get to the middle or middle vertex here, the apex of this triangle, it can't rotate in any way because there is no radius for it to rotate it around. It's at 0. So this will stay stationary. And this is what's actually going to create that better illusion of it rotating around itself or on a fixed axis, not orbiting something. And to kind of illustrate it as if we were looking at it on the screen, we have the top of the triangle up here, the bottom left, and the bottom right. The bottom right we said is going to rotate in a circle. Same thing with the bottom left. But the top of this triangle was going to stay stationary. And you can imagine as these bottom 2 points rotate, the top's going to stay the same, which is going to create a better perspective of it rotating along its own axis. And you can think about this as, again, holding up an object and rotating it in front of you. As you rotate it, you'll notice that it rotates as if it has some y-axis going down it, and it respects that. It doesn't orbit it. It just rotates around it with its already positions in space. So this is what we want, and this is going to be, again, the simple fix to our issue. So to fix this, let's jump back into the code, and let's go to the main cause of this issue, which is going to be in our rotate function. So to counter this, what we said is we were going to set each vertices z value to be to 0. So what we're first going to need to do is I'm going to create a local variable here named tempz. And what tempz is going to hold is the current offset for which the z value or the vertices z value is. So we know right now that this value is 0.5. So going back to the diagram, this is going to move a vertex down to 0. We want to keep this offset here so that when we rotate this new point, let's say we rotate it right here, that point wasn't there originally. So by keeping temp z, we can add it back to where it actually is, which was right here. And so as this rotates, this is going to create a better illusion of it actually rotating. And we will know that 0, this vertex, the apex was at 0, so this won't rotate. And this is perfect because this will stay stationary as these other 2 points rotate as well. So hopefully you can see that there. So going back to the code, again, temp C will hold this vertex offset, and then we'll just subtract vertices Z currently from itself to get it to 0. And then again, we'll apply the rotations as we did before. And then when we get to actually overwriting those vertices with the new ones, when we go to overwrite Z, we just need to add temp C back to it again to put it back to its original position. Notice X stays the same because we haven't changed X position at all. We want X to stay the same. So now if we run the code, we'll see the same program here as before, but when we begin to rotate it, you'll see that the triangle rotates about a y-axis running down the middle of it, you can think of. It doesn't orbit some arc. So we can get closer and see that it rotates as well. And we can get farther and see the same thing as well. So this is going to be our working rotation in our perspective projection 3D renderer. So yeah, I wanted to do rotations today because in the next episode, we're actually going to be using almost everything we've learned so far to create a camera system. A camera system is going to allow us to now be able to look around in our 3D world, along with being able to move in this 3D world, which will create a better look and feel and give us that more in-depth 3D render or 3D perspective. So again, just using everything we've learned, hopefully in the next episode when we cover the camera, you can follow along with decent ease, as everything I've been doing up until now will be used and adopted into our camera system. So yeah, thank you guys for watching, and I will see you guys in the next episode. Peace.